Professor Van Harlingen, Donald Big R. Willett, Professor and Head of the Physics Department at the University of Illinois, Oliver E. Buckley Prize in Condensed Matter Physics, Fellow of the American Academy of Arts and Sciences, and member of the National Academy of Sciences. He's going to talk to us about phase-sensitive measurements of exotic superconducting quantum materials and hybrid superconductor devices.
Okay, well, thank you very much, Bill, and thank you to the organizers for inviting me. It's a great honor to be here to talk at this symposium, particularly to talk share the podium with our two Nobel laureates and my good friends, experimental colleagues whose work I admire very much. So my euphoria about being invited to this session dissipated rather quickly when I realized that I wasn't quite sure what I was going to say. It actually turned to a lot of fear. This is a very big topic, and one that I've been involved in really my whole life since I started working on superconductors. And I wasn't sure what I wanted to talk about. So what I did, I decided to step back and think about what has excited me about this field. And certainly, I'm excited by new states of matter, as we heard about in the first two talks. I mean, who isn't? Something to discover new states of matter. I'm very interested in the quantum phenomenon that Cam Muller talked about right before me. And I'm very interested in quantum applications, that you're going to hear about in the last two talks. But what has really fascinated me most about working in this field is what kind of new experimental techniques can we develop that would actually help inform us about the nature of these materials. So today I'm actually going to talk about a technique. I'm going to talk about the powerful technique of Josephson Interferometry, which has yielded, I think, very important information about the phase properties of quantum materials and quantum phenomena. And specifically, I'll talk about two things. One is the order parameter of unconventional superconductors, and following a little bit on Cam's talk, measuring the current phase relation of Josephson junctions that have very unconventional barriers. So I have two kinds of friends in Urbana. I have theorists who come to me with new ideas. And when they come, I try to figure out what I can do with Josephson Interferometry to tell them something unique about the material or the phenomenon that they're studying. And I have experimental friends, and they come to me with new materials. And my thought process goes something like this. Is it superconducting? If it is, could it be unconventional or exotic? If it is, I want to measure the pairing symmetry. If it's not, go away, I don't really care. If it's not superconducting, I'm slightly disappointed, but then I start to think, can I make it into the barrier of a Josephson junction? Can I couple it, proximitize it with superconductors, in which case I want to measure the current phase relation. If it doesn't do that, again, I don't really care. So in my world, this is sort of the equivalent of saying when all you have is a hammer, everything looks like a nail. In my case, as a disciple of John Clark, everything to me looks like a squid. Okay, so let's go to the Josephson effect, which Cam introduced already a little bit. There's Brian Josephson when he was, where my mouse is here. I have no mouse. Okay, I'll point up here. So that's what he looked like when he discovered the Josephson effect. This is what he looked at his 50th anniversary of the Josephson effect, which I had the pleasure to giving a talk in. Very interesting symposium. And the Cooper pair tunneling, Josephson effect consists of Cooper pair tunneling that depends on the gauge invariant phase difference. And in the conventional form, it has this sinusoidal current phase relation. But as Cam already pointed out, there are cases in which it can be periodic, but very unusual, have higher order harmonics. This is what we define as the current phase relation. Now, a couple things you need to know about the Josephson effect. It's a local relationship, so it depends locally on the phase difference at the point in the junction. It's phase coherent, so to determine the critical current of the junction, you have to actually then actually look at the integral across the current phase relation across the junction. And it's also dynamical. Even though we mostly make measurements at DC voltages, squids and Josephson junctions are always dynamic because the phase winds when there's a voltage according to the Josephson relation. So here's an example of a Josephson junction. And this is two superconductors with an insulator barrier. And if you put a magnetic field into the screen, then what you can do is determine the critical current of the whole device by starting with the critical current at one point in the device, and then measuring that will determine the phase everywhere across the junction. There'll be a gradient in the phase across the junction determined by this equation. If you have a uniform magnetic field, then you get a linear phase variation. And that means the current is different at various points in the junction. And if you integrate that, you can see that it just turns out to be the Fourier transform of the current density, and you get this very familiar Fraunhofer diffraction pattern, which should be very familiar to you from optics. In fact, a very nice way to think about Josephson and squid devices is an analogy with a single slit or double slit interference pattern in which the intensity variation across the slit exactly mirrors the critical current of the junction. So here's a more elaborate equation, and this equation shows you how you can modify this equation, and actually everything I've ever done in my career is buried into this equation. You can look at critical current variations locally, things like gap anisotropy, domains, charge traps. You can look at the magnetic field term and look at things like vortices and magnetic particles. But today I'm going to talk about the two things in the middle of this equation. What happens when you change the current phase relation and get non-sinusoidal terms. And then I'm going to look at what happens when you introduce additional phase shifts into the interferometer by means of an unconventional superconductor. Okay, so when I was a student, like many of the students out here, superconductivity was actually a lot simpler. It was actually considered to be pretty much a solved problem. The transition temperature had grown up to only about 23 Kelvin. The BCS theory of superconductivity done in Urbana had explained what the phenomenon was. Electrons pairing into Cooper pairs due to this attractive force mediated by phonons. You had a condensate into a single phase, the phase we've been talking about, and that condensate can carry a supercurrent. And the pairing was known to be isotropic. In other words, the same in all directions of K-space, and you could measure that very nicely by looking at tunneling and measuring this very nice energy gap. It was so much solved that I was advised by more than one person to get out of superconductivity. It's a solved problem. Well, I didn't, and I'm glad I didn't, and everybody in here is glad too, because everything changed when high-temperature superconductors were discovered. The transition temperature, this was in 1986, what is that? Wow, 30 years ago. The transition temperature shot way up, and many of us, I think, who grew up in the 60s remember the Woodstock of music. How many people were at Woodstock? Probably nobody here, but a lot of people claim they were. But a lot of us were at the Woodstock of physics, which happened about 30 years ago at the March APS meeting. The Woodstock of music was 3 days, 33 acts, 500,000 hippies. The Woodstock of physics was 8 hours, 50 talks, and 2,500 physicists. It was great. How many people were at that event? And remember it very warmly, right, I think. I remember Bertrand Batlogg saying, our lives will be changed. Well, maybe not for everyone, but certainly for physicists, because it really changed everything we thought about condensed matter physics, materials research, and superconductivity. So high TC has many amazing phenomena, many of which are still unsolved. Many people consider it the biggest unsolved problem in condensed matter physics, and probably always will be. So, but the thing I want to talk about is unconventional superconductors, what happens in the dome of the superconductivity. And if you start to think about what that means, what we mean is not BCS, but in particular something which has an anisotropy in the magnitude or the phase of the order parameter. I think the first material we really knew was unconventional was uranium platinum-3. I'll come back to that one in a moment. But YBCO was the first one that was confirmed, and was expected to have this dx squared minus y squared pairing symmetry, which means the pairs act differently in different directions. So how do you determine the pairing symmetry? That's what the activity was kind of at that point in condensed matter physics. So this is what I always like to look at. It's a roadmap. What you do is you write down all the possible pairing states, including ones that are even symmetry, odd parity, even parity, odd parity, complex order parameters, and you write the magnitude and the relative phase as a function of K-space position. And if you do that, you can do experiments. So magnitude measurements, which are most experiments are, essentially probe the number of quasi-particles. So they can determine where you are in these different pictures. But one of the problems with those kind of measurements is because they count quasi-particles, they can very easily be fooled by things that mimic and sometimes mask the presence of nodes. So the phase measurements were really a more clear way to determine the pairing symmetry. And this is what prompted us to develop this phase interferometer technique I'm going to talk about. At that time, the two main candidate states were the D-wave superconductivity and the S-wave superconductivity and D-wave superconductivity. The big difference is in whether there was a phase variation in the order parameter. So the technique we came up with, actually suggested to us by Tony Leggett, is really simple. It's an interferometer. You measure the phase the way you always do in superconductors, in quantum materials. You put Josephson junctions on a crystal in two different orthogonal directions. Those probe the directionality. Because they're directional, they probe the k-space direction in different directions. You form a DC squid. By looking at the properties of the squid, you can determine what the properties of whether there's a phase shift in the quantum material. So you can, again, do this, think of this in analogy to single slit interference. If you have a squid, if it's a S wave, you'll get a periodic modulation. If you change the order parameter in part of the junction, just on one face, this isn't very bright here, then you can see the fringes shift. If you do it for a single junction, the Fraunhofer pattern modulates into a very distinct pattern. So experimentally, we did the experiment on squids, and you can see the phase shift here, indicating a D-wave superconductivity over here. And you can see it, do it in single junctions and see this very precipitous drop, very precipitous drop in the critical current, which is a strong signature of dx squared minus y squared symmetry. There were very shortly after after that some very elegant experiments. The tricrystal ring experiment done by the IBM group. You can make little rings like Cam was looking at, and you can use a scanning squid microscope, and you can either see a signal or not a signal depending on whether you have an odd number of junctions and you get a pi phase shift. A very nice experiment done by the Augsburg group was to make a squid in this fashion, and you can see here directly the shift in the interference patterns as you put a pi shift in or not. So you can either have two zero junctions or a phase shift of pi inside the junction. Another nice experiment was a grain boundary junction. If you make a junction where the lobe of the order parameter points into the node, you would like to think that the critical current would go to zero, but that's not what happens. What happens is you have facets along the junction, so the current actually alternately goes in different directions, and you get what looks like a multiple corner junction experiment, and you get these very characteristic patterns, which are characterized by, try this one. Here we go, that's better. Which are characterized by a lot of modulations, critical current, which is maximum someplace other than zero magnetic field, and it's highly symmetric with respect to field polarity. If you had an S-wave superconductor, this junction would give an enormous field going way up like this, an enormous critical current at zero field. So many experiments on cuprates have pretty much told us the same thing. They are always D-wave. All of them are D-wave. They're D-wave all the time. And and that's not for lack of trying. We've tried to do everything we can to this state. We had a proposal for a long time we called the fragility of unconventional superconductors. It was believed that unlike in S-wave superconductors, where scattering doesn't do anything, the so-called Anderson theorem, if you look at the 110 interface of a cuprate, you should always get a sign change, a phase shift of pi, and that should give rise to the zero energy bound states at this interface. The thought was they would coalesce together, nucleate into a superconducting phase, and form some kind of a complex phase integral. When the D-wave order parameter dropped, there would be some other term coming in and a complex order parameter. We were able to test that actually with Josephson Interferometry. This is an experiment where we used the asymmetric grain boundary junction. The prediction was that even a very small amount of complex order parameter would give you enormous change. It would do two things. It would lift the zero field critical current enormously by lifting the node in this direction, and it would break the symmetry, polarity symmetry of this device. Experiments done in my group indicated that this was not the case by William Niels and others, and you can see that over a wide temperature range, the shape of the critical current diffraction pattern does not change. So this state is simply not there. But luckily, there are other superconductors that are complex. I spent a lot of my career trying to look for these. The two big candidates are heavy fermion superconductors and the ruthenate superconductors. Heavy fermion superconductors, I should point out first that the way you can tell this is if you have a phase shift other than zero or pi, you get some kind of a shift that's between zero or half a flux quantum. If you have a magnetic flux, if you use a single junction, you see this node lift in the middle, or depress in the middle, as we said before, but in all cases, you get something that breaks polarity asymmetry. So here are experiments on UPT3 using beautiful single crystals from our chairman, Bill Halperin, and done by a student of mine, Joel Strand. In edge junctions, here's a junction on the edge, a junction on the corner. The edge junctions show Fraunhofer-like patterns. The corner junctions show a definite polarity asymmetry, which is indicative of a complex order parameter. And we were able to actually do experiments directly to see the node lifting and see that this material actually has two distinct order parameters, superconducting order parameters, one of the few materials still known to exhibit that phenomenon. You can see here the turning on of the critical current if we look into the lobe, and the lower critical current if we look into the node of the superconductor. The other interesting experiment we did was on strontium ruthenium oxide. This is my favorite superconductor of all time. This material is phenomenal, has really something for everyone, beautiful single crystals from Yoshimeno. In this experiment, we saw something we had never seen before. We saw hysteresis and very abrupt switches in the critical current as we measured this. And by thinking about this, we realized this could all be explained by having a chiral superconductor with domains, chiral domains, px plus ipy, px minus ipy. And so you could design, such as shown here, and you could design an experiment to test this directly, which is sort of a modification of the corner squid. If you look along, if you have domains of this type, then, as often happens in the cuprates, in one direction they align and you get very large critical currents in a Fraunhofer-like pattern. If you look in the other direction, they're out of phase, and you get a very suppressed critical current, about 100 times smaller. And you can see that it has this modulation form reminiscent of a grain boundary junction, again showing this chirality and the presence of domains. Now, there's many other things we're looking at in the pairing symmetry. Our interest right now is on topological systems, as has been pointed out in the previous talks. So a couple experiments we're working on now, and I don't really have all the answers to, but they show you, I think, things you can do with this technique. We're interested in looking at interfaces between superconductors and topological insulators. There are predictions this would give a p-wave term in the order parameter. That would show up as a deviation from the red Fraunhofer curve as shown here, and it would be symmetric. If you could break that polarity asymmetry, you might break that polarity asymmetry by injecting charge into this. That would pick one of the two spin pairing directions, and that would give rise to something which breaks time reversal symmetry. Another experiment is to look at a class of materials that are thought to be called topological superconductors. Candidates for this are things like copper-doped bismuth selenide and niobium-doped bismuth selenide. These are transport measurements from our group that show Andreev reflection. These materials show superconductivity. They show magnetism. They show Andreev reflection, gate-dependent surface currents, and hints of p-wave superconductivity in the tunneling spectra. We're right now trying to test the order parameter, doing a corner squid, corner junction experiment to see if these have a p-wave or odd symmetry type of order parameter. Okay, so let me go on to current phase relations, and I took longer in the first part because I knew Cam had already covered a lot of what I was going to talk about. I should say that if you look at this equation, changing the current phase relation does figure into diffraction patterns. In fact, you can see very clearly if you have add a term in, say, 2 phi or 3 phi, or both of those, you can see how the diffraction pattern changes. But if you look at things like the skewed current phase relation that she was referring to, notice that the superconducting diffraction pattern has not changed very much. This green is actually the deviation, and this is multiplied, in fact, by 10. So it's a very small change. So you want to measure the current phase relation directly, as she was pointing out in the previous talk. So there's lots of ways to do this. The technique that Cam has used was one developed originally by Larry Jackal and the Bell Labs people. This is where you inject a flux and look at the screening currents to detect that with a squid. The technique I learned about was when I was at Cambridge with John Waldron. It's sort of the current injection version of this. You put a current into the junction, divide it through an inductor. Basically, the current divides according to the phase, and by reading the current in the inductor, you can subtract that out and extract the current phase relation. There are high-frequency techniques, and I'm going to get to the point that I think she was heading toward, which is that frequency really matters in measuring these current phase relations in some cases. So this is a dispersive technique developed by Arnold Silver, Bascom Deaver, and recently exploited by Ilyushev. In this case, you drive an RF current, look at the screening currents, very much like in the screening experiments, but you do that at higher frequencies. And a very nice technique that I'm not even sure who originated, but it's kind of being used a lot now, is to make an asymmetric squid. And if you have a small junction and a large junction, then it turns out the modulation, if you measure the diffraction pattern, is almost totally dominated by the phase evolution of the small junction. So you can read the current phase relation out almost directly. All these techniques have in common that they're Josephson interference experiments. You have to somehow embed the junction in a multiply connected ring so you can track out the current phase relation. So I was going to run through a couple of quick examples. So Cam already talked about the nice work showing skewed current phase relations. This has been measured by our group using the interferometer technique. This is in graphene junctions, and you can see the skewness of the current phase relation and the temperature dependence of the skewness. There's been a recent paper by Nanda et al. Where they actually use this asymmetric squid technique and can directly track out, this is the modulation pattern, and it directly tracks out these skewed current phase relations. What I've been mainly interested in this space is the superconductor ferromagnetic superconductor junction. So when you have an interface between a superconductor and a ferromagnet, the order parameter not only decays, it oscillates due to the exchange interaction. And so if you can make essentially a particle in a box, a Josephson junction, where you have decay from both sides, you can have the possibility of a zero state, where you have a phase where the lowest energy state is a phase change of 0, or you can have a state where the lowest energy is a phase change of pi. And you can actually, as a function of the thickness of the barrier, you can move between those two and get this 0 pi transition. That's been measured by many groups. Another way to do it is to look at the temperature dependence, because it turns out these coherence lengths are actually dependent on the temperature, so you can take one junction close to the 0 pi transition and track out this transition directly. So a pi Josephson junction, just to make it clear, is actually a Josephson junction with a negative critical current. And the important thing about it is it has, as I said, a minimum energy at pi as opposed to a minimum energy of 0. So if you look at the current voltage characteristic of such a junction, what you can observe is as you change the temperature, the critical current comes down, goes to 0, and comes back up. But you can't tell whether there's a phase change or not. To do that, you have to use a current phase relation technique. So here are experiments where we, again, took a junction, embedded it in a ring, and here's the modulation patterns. You can see there's a modulation. It goes to 0 at a particular temperature, then it comes back, but notice the wiggles are out of phase by pi in this junction. So if you extract the current phase relation, you see it does indeed go from a sinusoidal current phase relation to no critical current at all to a negative critical current. So you can measure directly with the current phase relation this current phase relation pattern. Now, one nice thing about this, there is, of course, then a point where the critical current is 0. And when the critical current from the first order Josephson effect is 0, you're very sensitive to higher order terms. So we looked at junctions, and when the critical current goes to 0, we notice that there is indeed a small sine phi, 2 phi term. You can see it here. As the critical current goes to 0, it's periodic. Then it becomes doubly periodic, and then it goes back to being periodic again. So there is, in fact, a sine phi over 2 phi term. And this can come from rapid spatial modulations in the order parameter. In this case, they come from the fact that you're near this 0 pi transition. And so if the barrier thickness varies a little bit, parts of the junction are 0 junction, parts are a pi junction. And so what happens is, in this case, the first order Josephson effect cancels out, and you're left with a sine 2 phi term. This has been used very effectively recently. We've been looking at LBCO, lanthanum barium copper oxide, the first discovered high-temperature superconductor. Everyone abandoned that because it only had a TC of 30 degrees, but it's in fact more interesting than anyone thought. It has this very precipitous drop in the critical current, in the critical temperature, around 1/8 doping. And this is thought to be due to stripe phases in the pseudogap that freeze out. And there's been a proposal for a very exotic state called the pair density wave state by Steve Kivelson and Eduardo Fradkin, which is essentially an ordered stripe phase. And if you think about tunneling into this, you can see that along this edge, there's these stripes that have alternate phases, and so you're going to get a modulation in the sign of the order parameter. So we've been doing the anisotropic squid modulation experiments in our group. One of my students, David Hamilton, and we are now seeing some evidence for this as we go to change the temperature, and the critical current drops at higher temperatures. You can see it goes from a very clear sinusoidal current phase relation to something which has this other bump in here, and if you Fourier transform, it has a very distinct sine 2 phi term. So we think this is the first evidence for this pair density wave state. Okay, so Cam talked about topological junctions, so I'll go through this quickly. This is exactly what she talked about. If you have the junction of the system, we're interested in is a superconductor topological insulator, 3D topological insulator, superconductor junction. The current in this device is carried by Andreev bound states. At 0 pi, as you change the phase shift across the junction, this energy gap suppresses. And as she pointed out, you can get both skewed current phase terms that are high transparency terms, and also this very distinct sine phi over 2 term, which is a characteristic term of a Majorana fermion. The system we're interested in is when you apply a magnetic field and these Majorana fermions become localized in the junction. They enter the junctions just like vortices in a superconductor. And you can imagine experiments where you scan along the top. We're trying to do this and actually detect the zero bias states from these Majorana fermions. We like this system because you can actually move the fermions. When you apply a voltage, the phase winds very quickly. You can move them around something like 1 kilometer per second, very fast. And you can imagine devices in which you can move them around and braid and do various kinds of nice experiments. So is there any evidence for these Majorana states? Well, we think there is. If you look at junctions of niobium, bismuth, celadon, niobium, we see a more or less Fraunhofer diffraction pattern. But note that the first node is distinctively lifted in this pattern. Here's one where we did a doping dependence, and notice that this node suppresses with dope. The lobe depresses with doping, but the node is not changed at all. And if you zoom in very close, you can see this has a lifted first node, hard second node, lifted third node, hard fourth node, lifted fifth node. So it does appear to have this even odd effect. So this is appealing to us because it indicates that, so one way to get this would be to have a sine phi over 2 term, because in order to get a node, you have to cancel out both of those terms. This is not a very realistic model to have a uniform sine phi over 2, because we really only have Majoranas at various fixed locations in the junction. So a better picture is to think about a complex order parameter, not complex, complicated order parameter, which has a peak, has a term in sine phi over 2 at discrete phases in the junction. And so the overall current phase relation looks like this, and notice that it is 4 pi periodic. If you take that and you calculate the diffraction pattern, you see this pattern I suggested, a lifting of the first node, hard second node, lifting of the third node, and so forth. Okay, so that's some evidence, and so the question becomes, why can we see this? If you expect to have parity transitions between states, but we can really see it for 2 reasons. One, we cancel the first order Josephson term, getting rid of a lot of other things in the junction. And secondly, we go very fast, as Cam was pointing out. You have to go fast enough that you stay, you keep the parity the same and don't allow parity transitions. You can do that by measuring the diffraction pattern because you're actually biased in a finite voltage state. So even though you're measuring DC voltages, the Josephson frequency is actually in the gigahertz or sometimes even terahertz. Okay, so what we're doing now is to try to do current phase relation measurements. So if you do it slow with the interferometer technique, you indeed do not see anything. You don't see any evidence for 4 pi periodicity. We do see some skewness. This is very slow because you expect a lot of parity transitions. If you do it fast with, say, the anisotropic squid, we would expect to see something. In this case, we see distinctly skewed current phase relation. And you can make up your own mind if these little kinks here mean anything. This data was sent to me last night by my graduate student, so we haven't had time to analyze it. So I'm done, Bill. Takeaways from this talk. First of all, phase-sensitive Josephson interferometry is a very powerful technique to look at quantum materials. Secondly, there are many approaches to be a successful researcher. One is to find some technique that you can do over and over and over and make a difference, and that's a good advice, I think, for the students. Third, I have to rethink one of the guiding principles of my research career. One of my favorite sayings is, the farther you are from theory, the closer you are to a Nobel Prize. I think this symposium definitely proves that wrong. Two theorists, 2 Nobel Prizes, and there should have been 3 if David were here, and 4 experimentalists, no Nobel Prizes. So I'm going to make friends with a theorist when I get back to Urbana. Thank you.
Thank you very much, Professor Van Harlingen. Do we have a question for Dale? Yeah, we can't hear you. You have to come up.
When I was young, The reason it never happened. We never invented a superconductor which goes higher than room temperature. Are we closer to a room temperature superconductor?
Well, we're closer than we were when I started my career. It's interesting to point out that although we thought about the period of BCS superconductors where it got stuck for a lot of time, the highest transition temperature has been stuck with mercury compounds for now a longer time than in any period in the history of superconductivity. So I don't think we're close, but I do think there's a lot of opportunity to make things out of what we do have, which are high temperature superconductors. There are already power lines and power grids, and I think with maybe a different president, we'll be able to do that. I can feel myself being twittered about as I sit here.
Do we have any more questions for Dale? All right, thank you. Thank you very much again.